Well, I'm just verifying. That's Tristan Miller. So I already started off by writing the problem down. And the problem statement reads, potential flow against a flat plate can be described with the function psi is equal to a times axy, where a is a constant. This type of flow is commonly called a stagnation point flow, since it can be used to describe the flow in the vicinity of the stagnation point at point 0. By adding a source of strength m at point 0, stagnation point flow against a flat plate with a bump is obtained. Determine the relationship between that bump height, h, the constant a, and the source strength m. So I've already gone ahead and drawn the pictures of the potential flow. The first one, A, is the potential flow pertaining to a flat plate. And the so the net function, the net stream function actually that we want to obtain is psi is equal to psi on the flat plate. And we also now have to consider the source portion of the stream function. So we need to account for that and add that in there. So psi for the source. And we already know the psi function for the flat plate because it's given up here in the problem statement. And for the source, we know that it's given that the stream function for a source is m over 2 pi times theta, which is in polar. So I believe throughout this problem, it would be much easier to work in polar coordinates, which is why I think that our next step is going to be to switch our original potential stream function into radial or polar coordinates. Excuse me. So now we'll write out our actual two formulas. Flat plate is equal to axy, and in polar coordinates, x is equal to r cosine theta, where y is equal to r sine theta. And then we have this for the source is, like I said earlier, m over 2 pi times the angle theta. So all this together, we're going to get psi resultant, essentially, is going to equal ax, before transferring to polar coordinates, this is going to be axy plus m over 2 pi times angle theta. Okay, and then we're going to sub in down here x and y, oh my bad, x and y into the equation here. So we're going to get resultant is going to equal a times r cosine theta, r sine theta, plus m over 2 pi times theta. Okay. So now we can simplify further. It's equal to a times r squared times cosine theta sine theta plus m over 2 pi times theta. Okay, and from this, recall, I'll put this in red, recall double angle identity to simplify further. Let's see here. We have that sine 2 theta is equal to 2 cosine theta sine theta. Okay. So now that we have this relationship for the double angle identity, you can simplify further by simply dividing by 2, in which we will be able to simply just replace the entire cosine theta sine theta with just sine of 2 theta by just including a 1/2. So that would look like this, something like this. Resultant is equal to a over 2r squared, and that cosine sine theta can be replaced by sine of 2 theta plus m over 2 pi times our theta, and this is our stream function relating these two potential flows in which we can relate them to one another. And by doing, in order to do this, we're going to need to derive the velocity in the radial direction as well as the angular direction, since we're dealing with polar coordinates. And we know this stagnation point, the velocity in the radial direction is 0, and we can also replace this height with the radial direction and make the relationship with the height bump, or the height of the bump, with the constant a and the source strength. So from here, we can calculate the velocity in the radial direction. I'll indicate that little arrow here. Okay, and that is equal to 1 over r times the derivative of psi with respect to theta, which is equal to 1 over r, derivative with respect to theta of our function a over 2 r squared sine 2 theta plus m over 2 pi times theta. And since this is with respect to theta, the r can stay out front. The a over 2 r squared is just a constant, so that can stay there, r squared, and the sine of 2 theta just becomes cosine of 2 theta after taking the derivative multiplied by 2, taking into account the chain rule, plus the theta here just goes to 1, so you just end up with m over 2 pi, and that it ends up being your, oh, and these 2's can actually cancel out, which you end up getting 1 over r times a r squared cosine 2 theta plus m over 2 pi. So that is our velocity in the radial direction. And then we can also determine the velocity in the angular direction as well, because we can, in fact, find this angle here because we know where the stagnation point is located, which again is right here at the top of the hump. So to find the velocity, to find the velocity angular direction, it's simply delta phi, negative delta phi with derivative of phi with respect to r, which is equal to negative delta with respect to r times the equation a over 2 r squared times the sine of 2 theta plus m over 2 pi theta. And taking this with respect to r, I get v theta is equal to negative. So the a over 2 sine of 2 theta can come out front because that is a constant in this case. And then that's times 2r plus this whole thing actually goes to 0 because there's no r. So this can actually go away, which is equal to, these 2's will cancel, negative a r sine of 2 theta is equal to the velocity in the angular direction. Okay, so now that we have both of these equations, and looking at this particular graph down here, we already know that h is actually the radial distance here, so we can replace h. We can replace h or r with h, and we also know that the angle theta is equal to pi over 2 radians, or 90 degrees from right here, from the graph. And we also know that the stagnation, or the velocity at this point here, velocity in the radial direction is going to be 0 because this is a stagnation point. The incoming flow is going to have to stop here, and then it's going to converge down the sides of this bump here. So continuing on, we know that the velocity in the radial direction is equal to 0, and we actually have some points here. So r theta, we know this is equal to h 90 degrees. So substituting in, we know that velocity in the radial direction is equal to 0, which is, oh, let me highlight this equation here as well. And we know that the velocity in the radial direction is equal to 0, and we can sub in the r value and theta values that we have to solve the height of the bump in terms of the source strength and the constant A. Okay, so we do this by setting this equal to 1 over h in our case times a h squared cosine 2 theta plus m over 2 pi. And we can multiply h by both sides. That becomes 0, so you're going to get 0 is equal to, a h squared cosine 2, in this case theta is pi over 2. Cosine 2 times pi over 2, and these 2's are going to cancel, plus m over 2 pi. So, and after we simplify this a little bit further, down to the point of ah squared times the cosine of pi plus m over 2 pi. So you're going to get 0 is equal to the cosine of pi, which would be x, y, negative 1. So you're going to end up getting negative ah squared plus m over 2 pi. You can bring the ah squared over. So you're going to get ah squared is going to equal m over 2 pi. Divide each side by a. Divide each side by a. A over 1, so multiplied by, so 1 over a. And you're going to get h squared is going to equal m divided by 2 pi times a. So h is going to equal square root m over 2 pi a. And that's how you would relate the height of the bump, the source strength, and the constant A in this equation. And here is my signature to verify that this is my work on